Hi, I'm Chris Muchler, Principal Enterprise Architect and VCDX 257 from virtualelephant.com, and welcome back to my Network Fundamentals training course. In this course, we've been covering various topics to give you a solid foundation in the world of networking. And in this module, Module 4, we're going to be covering everything to do with L2 switching. Let's get started. So welcome to Module 4 on Layer 2 switching. So L2 switching is the process of forwarding Ethernet frames within a local network segment based on the MAC addresses. And switches are going to maintain different MAC address tables to make forwarding decisions efficiently. They're going to reduce network congestion and then provide a high level of network performance. Additionally, features like VLANs and loop prevention mechanisms are commonly used in L2 switching to enhance network functionality and reliability. So we're going to talk about 7 parts of L2 switching at a high level right now. So the first is frame reception. So L2 switches are going to operate at the data link layer, or the layer 2 of the OSI model. And when an Ethernet frame arrives at a switch port, the switch is going to examine the frame's destination MAC address. And then the MAC address is going to be used to determine where the frame should be forwarded within the local network segment. The second thing we need to know about switches is that the MAC address table is critical. So the switch is going to maintain a MAC address table, which is also sometimes called a MAC address forwarding table or CAM table, that maps MAC addresses to the physical switch ports. Initially, when the switch first turns on, this table is going to be empty, and as frames are received, the switch is going to learn and populate the table by associating MAC addresses with the incoming port. The next function that L2 switching takes care of is forwarding decisions. So again, when a frame arrives, the switch is going to check the MAC address table to find the associated port for the frame's destination MAC address. And if the destination MAC address is already in the table, the switch will forward the frame directly to the corresponding port. If, however, the destination MAC address is not found in the table, the switch will then forward the frame to all ports except the source port, and this is called flooding. The switch is also going to handle frames destined for broadcast addresses, things like ARP requests, by broadcasting them to all ports in the same VLAN. The fourth function that happens at the L2 layer with switches is around the broadcast and multicast handling. Now, broadcast frames are going to be sent to all devices within the same broadcast domain or VLAN. Multicast frames, however, if they're supported by the switch, are forwarded to specific ports that belong to a multicast group. Number 5 is frame filtering. So switches are going to filter frames based on the destination MAC address like we've mentioned. Frames intended for a specific device are delivered only to that device's port, reducing unnecessary traffic on the network. If you've been around in networking long enough, you might remember hubs, and this is a distinct difference with how switches operate in comparison to hubs. The sixth thing that we should be aware of is loop prevention, and we're going to talk more about this in a few moments. But L2 switches are susceptible to loops in the network topology, which can lead to broadcast storms and network instability. So spanning tree protocol is used to prevent loops by identifying and blocking redundant paths in the network. Now, the final piece to be aware of with L2 switching are VLANs. L2 switches often support VLANs in modern networks today, which is going to allow the network to be logically segmented into multiple virtual LANs on the same physical hardware switch. And each VLAN is going to operate as a separate broadcast domain, and switches can route traffic between VLANs when necessary. This is called L3 switching. Now let's dive a little bit deeper into the frame reception. So the frame reception has 5 parts: address learning, the MAC address table, frame filtering, broadcast and multicast handling, as well as loop prevention. And we've spoken a little bit about this just a moment ago. Now, the important thing to remember about the address learning is that this is the first thing as a frame comes into the switch that's going to happen. So the first thing it's going to do is it's going to determine what is the source MAC address of the incoming frame and what is its associated source port. And then it's going to determine if it already has that MAC address in the MAC address table. Now, as I mentioned a moment ago, the MAC address table is also sometimes referred to as the CAM table, which stands for Content Addressable Memory. And again, these mappings are going to correspond to physical ports on the switch, or if it's a virtual switch in a vSphere environment, a virtual switch port. But essentially, it's going to be a one-to-one mapping between the MAC address entry and the port that it's associated with. Now, once it's determined if the MAC address is in the MAC address table, the next thing it's going to do is actually filter the frame. And now this is going to be where it makes a decision on where to actually send the packet next. So if it's the next hop, it'll send it to another device. If the packet is destined for a port on the switch, for example, another physical server, it'll get forwarded out the port that physical server is attached to and the MAC address is in the MAC address table for. Now, if once that's done, there's going to be some sort of broadcast frame that's going to be sent out if it needs to determine where to send everything. And then the final part, again, is the loop prevention to make sure that the packet isn't just going around in a loop. Now, this used to be more common in core access networks. Spanning tree protocol was used heavily in those types of networks. But as we've migrated more and more to spine leaf networks, spanning tree protocol has become less necessary because it's almost impossible for a network loop to occur in a spine leaf architecture. Now that we understand more about the frame reception, the next thing that I want to spend just a moment talking about is the MAC address itself. So on the screen here, you actually see an example MAC address. So the thing to remember is that a MAC address is a 12-character hexadecimal address with the first 6 characters on the screen here that you see 005056. Those are going to be unique organizational assignments. So the 005056 that you see here, these are for VMware MAC addresses that will get created for a virtual machine within a vSphere environment. So whenever you create a VM and you look at the network controller on that VM, you'll see that the first 6 characters are if it's 005056. Now the second 6 characters, the ones that you see here on the screen represented by F1, 4C, C6, these are going to be network interface controller specific. So these are going to be randomly assigned if it's a virtual machine, and if it's a physical device like a NIC in a bare metal server, then it's going to be something that the hardware manufacturer allocates to that physical device. And again, these should be unique. It is possible for there to be duplicate MAC addresses. It does happen, especially in cloud and virtual environments. And if that's the case, then you need to change the MAC address based off of whatever the capabilities are of your virtualization provider. Because if there are duplicate MAC addresses, just like if there are duplicate IP addresses on the network, it's going to make it difficult for the packets to actually be sent to the correct device. And so you'll potentially see odd network behavior with packets going across the network, across different paths and not getting to where you think they're going to be getting to. And again, something like TCP dump or Wireshark, like we covered in Module 3, the MAC address will be captured and you can see the source and the destination MAC address in a packet capture. And so if you are having an issue where there is potentially a duplicate MAC address, that is one way that you can see and troubleshoot those issues. So now let's talk more about VLANs. So VLANs have become a fundamental feature in all data center networking today. And these are going to allow you to logically segment a physical LAN into multiple virtual LANs, a VLAN. And each VLAN is going to act as its own independent broadcast domain. And this is going to allow you as the network administrator to be able to isolate traffic and control network communications. So let's talk about isolation. So now devices within the same VLAN can communicate with each other as if they were on the same physical network, while devices in different VLANs are segmented and cannot communicate directly without routing or L3 routing. Each VLAN is going to represent a separate broadcast domain. And this means that broadcast traffic, such as ARP requests and DHCP requests, are going to be contained within its own VLAN, reducing unnecessary broadcast traffic on the network. From a security perspective, VLANs are going to allow us to enhance network security by isolating sensitive or critical resources from less secure areas of the network. Think of like a DMZ. And access controls can be applied to restrict communication between those VLANs, allowing further isolation. The final advantage that VLANs offer us is around performance, because by segregating the network traffic, VLANs can improve network performance by reducing broadcast and collision domains. Again, think about how a hub used to operate as a singular broadcast domain versus a switch today that allows us to be able to break up those broadcast domains across hundreds of devices that are physically connected to a physical switch. So moving on, we want to talk for a moment about the different VLAN trunking modes. So there are two different ways of doing this. And again, some of this harkens back to when the networking companies like Cisco were trying to have their own proprietary protocols versus the community coming up with a standard that all networking companies and all network devices could adhere to. So we have two different types of VLAN protocols. The first is the Inter-Switch Link, or ISL, and this is a Cisco proprietary trunking protocol, and it's going to encapsulate all of the Ethernet frames with an ISL header. But this is mostly obsolete today, but I wanted you to be aware of it so that you can again see that depending on when technology came out, we've seen different iterations of different technologies. And this is especially true even in the software-defined networking space, as we're going to talk about in a future module. Now, the industry standard is what's commonly referred to as .1Q, and this is referring to 802.1Q. And this is the industry standard trunking protocol for all VLANs. It's going to use a 4-byte VLAN tag inside of the Ethernet frame header, and it's been the most widely adopted trunking mode for all modern networks. So more than likely, this is the only thing that you're going to see in practical application today, but it's important to be aware that ISL did used to exist. So depending on the organization that you work for, if it's older, has legacy data centers, it is possible that you'll come across ISL for VLAN trunking modes. Now, the next major part that we're going to talk about is spanning tree protocol. So again, spanning tree protocol's primary purpose is to prevent and resolve loops in Ethernet LANs. So it used to be possible when you had a core access topology within a network, a data center network, that you would have multiple switches interconnected with one another, and it was possible that an actual loop would exist. And a packet could get stuck in a loop while it's looking for its final destination because it actually didn't exist. And so all it keeps doing is looping around all of the physical switches in an infinite style. And so spanning tree protocol was created to prevent those loops and broadcast storms from impacting our network performance in the data center. So first, L2 switches, okay? So L2 switches are going to forward those Ethernet frames based on the MAC addresses like we've talked about. And from there, this is where STP is going to step in. It's going to identify and block redundant paths to prevent loops while allowing network redundancy. So it will see that there's multiple paths to a destination. It will essentially mark one as the active or preferred path and mark the others as redundant until a time exists where that primary path becomes unavailable. And this is going to allow us to prevent that loop prevention in a core access topology. Because by placing those redundant links in a block state, only one path is going to be active at any given time. Now, as we talk more about some of the concepts within spanning tree protocol, you can see here that there are 6 concepts that we should be aware of: root bridge, bridge ID, the bridge protocol data units, or BPDUs, the path cost, a bridge priority, and the topology changes. So let's spend a few minutes talking about these components within spanning tree protocol. So first we have the root bridge. Now the root bridge is going to be that central switch in the STP topology. all switches in the network are going to elect the root bridge, and it's going to serve as the reference point for calculating the shortest path to reach all other switches within the topology. Then we have the bridge ID. Each switch in the network has a unique bridge ID, which is going to consist of both a priority value and the switch's MAC address. And then the switch with the lowest bridge ID is going to become the root bridge. Then we have the BPDUs. Now these are control messages that are going to be exchanged between switches to establish and maintain the STP topology. And they contain information about the sender's bridge ID, the path cost, and the topology itself of the network. We also have the path cost. Now each link between the switches has a cost associated with it, and this cost is going to represent the expense of using that link. And STP calculates the path cost to determine the best path to the root bridge. Then we have the bridge priority. Now this is going to be a value set on each switch to influence the election of the root bridge. Think of this as putting your thumb on the scale. Lower values indicate a higher priority. And then finally, we have topology changes. Finally, we have the topology changes themselves. And STP is going to monitor the network for changes, such as link failures or additions of new switches. And when a change is detected, STP reconverges to adapt to the new topology. And these STP reconvergences have been many a headache for many network administrators over the years. When you have a very large-scale enterprise network running STP and you add a new device, it's been known to cause pain during the STP reconvergence time. And so depending on how large your network is, you have to be aware of this because you can see poor performance across the network as STP reconverges. The final piece for understanding what STP is and how it operates are the different port states that a switch can be put into, and there are 4. So the first is blocking. Now this basically just means that the port is disabled, preventing any data from passing through it. Then there's listening. The port is going to prepare to participate in STP by listening for those BPDUs. And then learning. The port is actively learning MAC addresses and populating its MAC address table. And then finally, you see forwarding. The port is in the forwarding state, thus meaning that it's going to be allowing data traffic to pass through it. Now, when you're looking at STP states on a switch, you should really only see the first and the last, blocking or forwarding. The other 2 states are going to happen relatively quickly, and unless you're actively looking for it and checking the config, you might miss it. But if you're having problems with STP in your environment, the first thing that you want to look at is to see what state the ports are in. And if you see something in a listening or a learning state for very long, you likely have an issue with that port and the STP configuration that you need to go check and troubleshoot. So that concludes Module 4 on L2 switching. We've covered everything from MAC address tables to VLANs to spanning tree protocol. In the next module, Module 5, we're going to cover everything around L3 routing and what goes into getting a packet from point A to point B. Now, if you're enjoying this Networking Fundamentals course, please make sure that you subscribe to the channel and turn on notifications. Also, feel free to reach out to me on YouTube by leaving a comment or finding me on Twitter @ChrisMutchler. I look forward to seeing you next time.